This mechanical setup consists of three solid metal blocks connected by heavy springs, oscillating in a complex, non-repeating pattern. In this three-degree of freedom system, the motion of any single mass is immediately influenced by the forces exerted on it by the other two. This is the differential equation of motion for the system. The red highlights on the off-diagonal terms in the mass and stiffness matrices represent mathematical coupling. These non-zero terms indicate that the displacement and acceleration of each mass are interdependent, requiring all three equations to be solved at the same time. Solving these dense, simultaneous equations directly is computationally demanding and makes it difficult to isolate the individual behavior of each mass. Structural dynamicists address this by changing the coordinate system, moving from physical displacement to a set of coordinates where the equations become independent. By leveraging the property of mode orthogonality, this 3-DOF system can be simplified into three independent 1-DOF systems. This simplification is possible because of a specific physical property of mass and stiffness. Their mathematical representations are symmetric. If we assume a harmonic solution, the differential equation becomes an eigenvalue problem. Solving it yields three distinct mode shape vectors, labeled phi1, 2, and 3. These vectors represent the system's natural frequencies and its corresponding mode shapes, the specific patterns in which the masses move relative to one another. In structural dynamics, the term orthogonality is often misunderstood. It does not refer to standard geometric perpendicularity, as shown by this crossed-out dot product. The mode shapes of a vibrating structure do not necessarily exist at 90-degree angles to each other in physical space. Instead, these modes are independent only when evaluated through the mass and stiffness matrices. This is the definition of orthogonality in a dynamic system. Standard geometric rules do not apply here. The separation of modes depends entirely on the physical parameters of the structure itself. We can prove this by comparing the equations for two different modes, I and J. First, we take the equation for mode I and pre-multiply both sides by the transpose of mode J. We then do the same for mode J, pre-multiplying by the transpose of mode I. Both the mass and stiffness matrices are symmetric. This means the matrix is identical to its own transpose, effectively flipping across its diagonal without changing its values. Because of this symmetry, the left side of the first equation is now mathematically identical to the left side of the second. Subtracting one equation from the other allows us to cancel the left sides and group the remaining terms on the right. Since we are looking at two different modes with two different natural frequencies, the difference of their squares is not zero. For the entire expression to remain zero, the mass inner product term must be the part that equals zero. This confirms mass orthogonality. Plugging this result back into the original eigenvalue problem demonstrates that the same relationship holds for stiffness. The independence of these modes is a direct consequence of the symmetry found in mass and stiffness. To use this property, we combine these mode shape vectors side by side to form a single modal matrix, represented by the symbol phi. We define a change of coordinates, where the physical displacement u is replaced by this modal matrix multiplied by a new set of coordinates q. When we multiply the entire equation by the transpose of the modal matrix, we expand it into these two 3x3 grids. The orthogonality conditions we just proved now dictate the values within these grids. Any value located off the main diagonal represents a connection or coupling between different modes. Because of orthogonality, every one of those off-diagonal terms becomes zero. The interaction between modes disappears, leaving only the diagonal terms. By aligning our coordinates with the natural modes of the system, we have effectively removed the mathematical coupling. Finally, we scale the mode shapes so that the product of each mode with the mass matrix equals 1. This is called mass normalization. This step simplifies the mass matrix into the identity matrix, where only the main diagonal contains ones, and everything else is zero. The system of equations now splits into three separate, independent lines. Each describes the vibration of a single mode. The complex 3-degree of freedom system is now represented by three independent equations that do not influence each other. These individual equations can be solved using basic calculus, allowing us to predict the behavior of the entire structure without solving simultaneous equations. This simplification is rooted in the way a structure stores and moves energy. The mass and stiffness matrices are symmetric because they represent the system's kinetic and strain energy. In a linear system, the energy stored in a spring is shared between two masses, and the work done to move mass A relative to mass B is the same as the inverse. This physical reciprocity creates the mathematical symmetry we rely on. Because the physical energy of the structure is consistent, its complex vibrations can always be isolated and understood.